Okay, here I'm going to do Peleus problem 4.6. And maybe I'm getting better at this thing here. Basically, we've got a slab waveguide or a thin film waveguide. I'll call it a slab here. And we're looking for a range of thicknesses for which we have one mode for one wavelength and two modes for a second wavelength, a second shorter wavelength. So we're given lambda 1 is the larger of the two wavelengths, and lambda 1 is 1300 nanometers, and we're also given lambda 2 is 820 nanometers. And what we want to do is find the range of waveguide thicknesses giving one TE mode for lambda 1 and two TE modes for lambda 2. Hope this is readable here. Okay, so that's our problem statement. And basically what we'll do is we'll look at the cutoff condition. Let's make a quick sketch of the N effective versus d by lambda plot. So this is our mode plot. So this is d by lambda, and this is N effective ranging from N2 up to N1. And we're given N1 and N2 also. N1 is 1.48. I think they say in the book that you're supposed to use the slab waveguide from a previous problem. And N2 is 1.46. And so we have our cutoff for our zeroth order mode at d equals 0. The cutoff for the first order mode is at d by lambda is equal to delta, where as in a previous problem we have delta is delta d by lambda at cutoff, which is 1 over 2 square roots of N2 squared minus N. I've done it again. N1 squared minus N2 squared. And if we want the cutoff for the first mode, what we can do is simply solve for d here. What you find then is that delta, that we can make a picture showing as a function of the thickness of the waveguide d, we can plot out the d values at which the cutoffs occur. So here's 2 delta, where the m equals 2 mode starts to appear, 3 delta, where the m equals 3 mode starts to appear, and for a particular wavelength, these cutoffs occur at multiples of lambda times delta. So this is then, say, lambda 1 times delta, and here at twice this value we have 2 lambda 1 times delta. And so for d values less than lambda 1 delta, we have one mode for that particular wavelength. Now lambda 2 is shorter. It's only 820. So if I make a similar plot, this is again D now, but now lambda 2 being shorter gives me lambda 2 times delta being something less than lambda 1 times delta. And then at twice that, we have 2 lambda 2 times delta. And now what we're interested in is we're interested in the range of thicknesses, that is the range of D values, where we have 1 TE mode for lambda 1 and 2 TE modes for lambda 2. Well, 1 TE mode for lambda 1 occurs in this range, and 2 TE modes for lambda 2 occurs in this range. And so what we're interested in solving for then is this range of D values right here, where we have 1 mode for lambda 1 and 2 modes for lambda 2. And these two values are simply lambda 2 delta and lambda 1 delta. And so what we want then is to say that D is greater than lambda 2 delta, but D is less than lambda 1 delta. Okay? And let's see. Delta is this value, and so, well, if you plug in the numbers, basically, lambda 2 delta is lambda 2 over 2 square roots of n1 squared minus n2 squared. And you get, for that value, 1.69 microns. And for lambda 1 delta, we get 2.68 microns. And that does it. And so this little diagram here is really the key, realizing that you can move from a D over lambda plot, which works for any wavelength, to just a D plot showing the cutoffs. And for two different wavelengths, the cutoffs are occurring at different thicknesses. So that's 4.6.